Colligative properties are properties of solutions that depend on the concentration of the solute and not on the identity of the solute. Remember, the solute is the component of the solution that is in the lower quantity. The component of a solution that is in the higher quantity is called the solvent. The reason that solutions have these properties and pure solvents do not is because the solute particles get in the way of the solvent particles. The concentration of the solute and the solvent can be expressed in many ways: molarity, molality, mole fraction, and percent mass. We will be discussing all of these ways to express concentration in these colligative properties video. The first concept to understand is vapor pressure. Vapor pressure is the pressure and equilibrium above a liquid in a closed container at a certain temperature and surface area of the liquid. Think of it like this. If you leave a closed bottle of water on the counter, some of the liquid molecules are turned into a gas and are released from the top of the liquid. You can view this as condensation on the sides of the bottle above the liquid. Eventually, the rate of liquid becoming gas and of gas becoming liquid will be equal, and then equilibrium is reached. This is when the vapor pressure is read at a certain temperature. Which has a higher vapor pressure, ethanol or water? Or another way to think about this is which liquid will produce the most condensation above the liquid at the same temperature and surface area. We will answer this question in the first part of the next video. But when a non-volatile solute is added to a solution, the vapor pressure decreases. Non-volatile is another way of saying not able to be vaporized. So a non-volatile solute is something like salt or sugar. The vapor pressure decreases because the non-volatile solute particles will get in the way of the solvent particles that are being vaporized into the gaseous phase. A discussion of vapor pressure leads us right into Raoult's law, which was named after François-Marie Raoult, a French scientist who studied solutions' properties. Raoult's law states that the vapor pressure of a solution is the sum of the vapor pressures of each of its components. The vapor pressure of a component of a solution is the product of the vapor pressure of the pure component, the solvent, and its mole fraction in the solution. Remember, back in the concentration units video when I said that the mole fraction of the solvent becomes important, here's where this comes true. Only liquids can have vapor pressures, and most non-volatile solutes are solids. So to determine what happens to the vapor pressure when a solid solute is added to a liquid solvent, we need to consider the liquid solvent by calculating its mole fraction and multiplying it by the vapor pressure of the pure liquid. So for example, if we add a mole fraction of 0.5 solvent, then the vapor pressure will be half that of the pure solvent. Remember though, that vapor pressure of the pure liquid will change with the temperature and surface area of the liquid. Usually in problems that involve Raoult's law, they will have to give you the vapor pressure of the pure liquid. We can visualize vapor pressure by looking at a phase diagram. The phase diagram of a pure solvent, in this case water, is shown with the solid line. And the phase diagram of that same solvent with solute in it, a solution, is also shown with the dashed line. The liquid gas line is lower for the solution than the solvent. This is caused by the vapor pressure lowering of the solution. The solid liquid line is also different for the solution. Now we will introduce our next two colligative properties, boiling point elevation and freezing point depression. Looking at this same phase diagram, if you compare the boiling point of the solvent and the solution, you see that the boiling point is higher for the solution, and the freezing point is lower for the solution than the solvent. But why is this? The definition of boiling point is the temperature at which vapor pressure equals 1 atmosphere. The freezing point of a solution happens when the pure solvent turns into a solid. When you add solute particles to a solvent, the solute particles get in the way of the solvent. In the case of boiling point, when the solute particles are dissolved in the solvent cannot reach the surface in order to boil. Thus, a higher temperature is needed for the vapor pressure to reach the surrounding pressure, and the boiling point is elevated. In the case of the freezing point, the solute particles get in the way of the solvent again. Thus, it is more difficult for the solvent particles to find the ice cube, and the freezing point is depressed. Another aspect of colligative properties we haven't mentioned yet is how many solute particles are dissolved in the solvent to make the solution. In the case of anionic solids such as NaCl, There are two solid particles, one Na plus ion and one Cl minus ion. Both of these solute particles need to be taken into account, and they are with the inclusion of the Van't Hoff factor. The Van't Hoff factor for NaCl is 2.0, like expected at low dilutions of less than 0.01 molal. But when the concentrations of these ions is higher, some of these ions may stick together, lowering the Van't Hoff factor. The Van't Hoff factor becomes farther from the ideal, as this figure shows, the larger the charges on the ions. And the Van't Hoff factor is 1.0 for molecular compounds such as ethanol or sugar because they do not dissociate in water. The two equations that relate the boiling point and freezing point of a solution are similar. The equation is the change in temperature equals the Van't Hoff factor times the molality of the solution times the constant for the solvent. The constants are different if you are calculating boiling point elevation or freezing point depression. The boiling point elevation constant for water is 0.52 degrees Celsius per molal, and the freezing point depression constant for water is 1.86 degrees Celsius per molal. The two equations for boiling point elevation and freezing point depression are shown here. Most problems that are about boiling point elevation and freezing point depression will have to give you these constants for the solvent, and most problems will tell you what to assume for the Van't Hoff factor as well. The last colligative property to cover is osmotic pressure. Osmotic pressure is defined as the measure of the tendency of a solution to take in water by osmosis. Osmosis is best illustrated by considering a semi-permeable membrane separating a solution from the pure solvent, such as in the following drawing. Semi-permeable means that the solvent can travel through the membrane, but the solute particles cannot. Over time, the pure solvent will travel away from the side with the highest concentration of pure solvent, so it will travel to the solution side. Eventually, the rate of concentration-driven movement of the solvent particles toward the solution side is balanced by an opposing pressure created by the difference in the liquid levels in the sides, and an equilibrium is reached as shown in the drawing. The opposing pressure is called the osmotic pressure and is represented by a capital Greek letter pi. The equation for osmotic pressure equals the Van't Hoff factor for the solute times the molarity of the solution times the gas constant times the temperature at which the experiment is being run at. The Van't Hoff factor is included because osmotic pressure depends on the concentration of the solute. The gas constant and temperature are included because this equation is related to the ideal gas law equation. The gas constant has a value of 0.08206 liters times atmospheres per mole times Kelvin, so osmotic pressure is measured in atmospheres. This image shows what happens when a container of pure solvent, in the light colors, is placed in a closed container with a solution in the dark green. Eventually, the pure solvent will vaporize and migrate toward the solution container. Please watch the next video for example problems relating to colligative properties.